So let's talk about the cardiac action potential. All right, so when we looked at skeletal muscle, we put together this pattern where we get a rapid depolarization followed by a repolarization, hyperpolarization, and then return to baseline. Well, in cardiac muscle, we have the same general pattern, but we've added a component. We've added the plateau phase, which you see is at number 2. Okay. So here, what we have, if you look, these two graphs share the same axis. Okay. So here's time. Here's membrane potential. Now down here, what we have is membrane permeability or ionic currents, ionic movements. All right. So we can see that when depolarization occurs at 1, that depolarization is occurring because of a big inward outflow of sodium ions, just like we saw in skeletal muscle, right? All right, so we have our big depolarization. Now, at point number 2, though, instead of just having potassium channels open, we also add calcium channels, which are going to open at the same time. Okay? So, all right, so point 0 is our fast sodium channel, so big influx, B depolarization. At number 1, we get 2 things that happen. One is the sodium channels close, okay, inactivate technically. And number 2, the slow calcium channels open. Now, what's the trigger for that? Same trigger, big depolarization. It's just the calcium channels are slower to open than the sodium channels are, but same stimulus, membrane potential change. All right, so these slow calcium channels here, they allow calcium in and sodium in, but mostly it's the calcium that predominates. Okay, so they're slow to open. They stay open, though, for a good long time, 0.2 seconds. Now, this is critical because this action potential diagram looks very different than skeletal muscle, right? Skeletal muscle was just up and down, and that's it. Nerves, same way, up, down, and that's it. So this long plateau phase, it means that this whole action potential takes place over a much longer period of time than a standard muscle cell or nerve cell action potential, right? So it's 0.2 seconds, 200 milliseconds, as opposed to, 10 milliseconds. So there's a few important bits to this importance of this plateau. Number 1, function. It's during 2 that the calcium that triggers muscle contraction is entering the cardiac muscle cell. So you can imagine that's pretty pivotal. If calcium doesn't enter, the muscle doesn't contract. Now your heart's not doing its job. Okay? So that's point number 1, is that allows the calcium in. But the second thing is it means that the refractory period of cardiac muscle is much, much longer than skeletal muscle is. This is a good thing, all right? The heart can't contract effectively too fast, all right? When you get to heart rates above 140 or 150 in a human being, the heart doesn't have enough time to fill before it contracts again, and you start to get a drop-off in cardiac output. So having a longer refractory period forces our heart to beat a little slower than it could, but what we get out of that is more effective contraction, as we'll see when we talk about the cardiac cycle going forward. Okay, so calcium in, sodium in, they stay open for a long time. In terms of membrane potential change, right, we go from hyperpolarized to depolarized. Then we hover just above 0 at 2. And the reason we hover there is because of the calcium entering, and it's at 2+, and the concentration gradients. We just don't get a lot of big ionic movements at 2. Okay? And then, unlike skeletal muscle, the potassium efflux, how much potassium is leaving, is much less during phase 3 than it is, or it's much less during depolarization. And it's only triggered late, like in that point there. So Sodium is first and fast. Then there's a kind of potassium blockade where potassium just isn't moving very much, right? You can see that here. This is the blockade. That our outward flow of potassium originally, it slows to almost zero when calcium is entering. Do you see that? So potassium blockade, then calcium influx, then potassium efflux at the end, right? So you can see potassium permeability increases at about the same time that the plateau turns into the repolarization curve at 3, right? And then 4 is our refractory period. All right, so there's a lot in this one diagram. And the most critical part of the whole thing, there's 2 important parts. One is you have to get the cell to depolarize. You have to get it to do something. That's the sodium channel, right? You got to make a depolarization happen. Number 2, once you've triggered something, you need contraction to happen. So once we have our depolarization, we need to open our calcium channels in order to get calcium entering the cell and contraction to start, right? If you don't have both of those things, you're not going to have cardiac contraction like you need it. All right. Okay, so the plateau causes the action potential to be much longer than skeletal muscle. See, I get ahead of myself. I did that already. So cardiac muscle contracts slower. It has a much longer twitch time. A twitch is just a muscle contracting and relaxing, right? Skeletal muscle, particularly small skeletal muscles like your eye muscles, can twitch very, very fast. The heart can't, and this is a good thing. We don't want a heart that twitches, right? We want a heart that contracts and relaxes. So the plateau helps to make that possible. Now, cardiac cells also have a sodium leak, which exceeds the activity of the sodium-potassium pump. All right, so what does that mean? It means that if you put cardiac cells in a petri dish and you leave them alone, they're going to leak enough sodium out that they'll contract on their own. They will self-depolarize. This isn't a bad thing either. We want our cardiac cells to rhythmically contract. The reason they rhythmically contract is because they're leaky to sodium. When enough sodium leaks out, they reach their threshold potential and then they contract, right? Then you get the action potential, things go back to normal, and then the same thing happens again. Okay, so cardiac cells depolarize spontaneously. Now the rate of depolarization increases. And we're going to talk about this as the train analogy later on. But so cells from the SA node, the SA node is the control center of the heart, right? It's what triggers normal contraction. The SA node beats fastest, right? The atrial cells beat next fast. The ventricular cells beat very slowly compared to atrial cells. Now, is that what's happening all the time? Of course not, because all the heart cells are contracting together. But if you plucked a ventricular cell out and put it in a petri dish, and plucked an atrial cell out and put it in a petri dish, the ventricular cell would beat much slower, right, than the atrial would. We'll put all this together into an actual human being when we talk about the conducting system. All right. Okay, so here we go. I didn't talk about this chart yet. So here we've got force of contraction and we've got seconds, okay? So what we can see is that the heart muscle, it can't have another contraction here because it's already in its refractory period. Now, in this little area, it could technically have another contraction here like it does here, but the second contraction will be less vigorous if it's too early. So what this is showing you is here's a contraction. Here's a contraction with a second one that came too soon. So you can see that the second one's force is quite a bit less. And then here we have another premature ventricular contraction, but they're about the same size because it happened after the refractory period. I actually think that talking about cardiac rhythms in terms of refractory period is very confusing. So don't worry too much about that bottom graph, all right? we're going to build it more naturally when we look at the conducting system and when we put it all together.